a video for Advanced Algebra 1. We are progressing into topic 5, section 1, and it starts out with the absolute value function. And, right now we have focused on graphing linear equations. Y equals mx plus b, graph the intercept, use the slope to find another point, et cetera, and so on. But when we started graphing linear equations, what we actually started with was just making a table of values and then plotting those points and determining what the graph looked like. So, and that will always work. Whenever you have y equals something and you don't know what the graph is supposed to be, then you can just plug in numbers, make a table of values, plot the points, and determine what the graph would look like. So that's what we're going to do here for this first one. And the most simplistic form of the function, whatever you want to call it, is what we call the parent function. So when we were graphing lines, the parent function was y equals x. Then when we moved it to y equals x plus 2, that translated the graph on the coordinate system. Or 2x minus 4, and that translated it in a couple of different ways on a coordinate system. So this is following a mini project of graphing functions and looking at the various types of graphs from their parent functions and how they move, and hopefully the way that we graph those was just by making tables of values. So again, that's just what I'm going to do here. We are graphing f of x, or y equals the absolute value of x. And so I am just going to make a table of values. So if I plug in 0 for x, the absolute value of 0 is 0. If I plug in 1, the absolute value of 1 is 1. If I plug in 2, the absolute value of 2 is 2. And if I plot those points, 0, 0, 1, 1, 2, 2, I don't know if that's all my graph. I know that if I plug in 3, I'm going to get 3. If I plug in 4, I'm going to get 4. But I need to know what the other side of the graph looks like as well. So I need to plug in -1. And the absolute value of -1 is +1. And I need to plug in -2, and the absolute value of -2 is +2. And so the other side of my graph, -1, 1, -1, 2, if I plugged in -3, I get 3. The other side of my graph looks like that. So then this is the graph of the absolute value. Okay? And this point down here for this graph at 0, 0, that would be the vertex of the graph. There is a thing called the axis of symmetry. The axis of symmetry goes through the vertex, okay? And these are mirror images of each other. If I have a point over here, then I'm going to have a point over here. If I have a point here, then I'm going to have a point here, et cetera, and so on. And it goes on like that. So there is an axis of symmetry here. If I fold this graph over, it lands on itself. Okay. Domain is something that we talked about with linear functions a little bit. The domain corresponds to the x values of the function of the graph. And so for this particular function, I can't get down there to where I wrote domain. We'll lose the picture of the graph, so I'm going to keep it like this. So for the domain, is there anything that I can't plug in for x? Can I plug in 10,000 for x? You bet. I'm not going to want to graph that. 10,000, 10,000? I plug in -500 for x. Yeah, the absolute value of -500 is +500. That exists, somewhere over there in Leroy, I think, on this graph. But anyway, the domain unless there's a restriction, domain for most of the graphs we're going to do, and again, coming off the graphs that we just did in the little mini graphing project, we know what the difference is, but the domain here is all real numbers. And one way to write that is to write all real numbers. Another way to write that is to use a symbol for all real numbers. And another way to write that is in bracket notation, and we write negative infinity to infinity using parentheses. And that means, anything from negative infinity to infinity can be plugged into the graph. And that's a way of saying all real numbers. Okay, this bracket notation they do use sometimes on the questions online, and we have run into that. So there it is again. And then we like to talk about the range with these functions. And the range corresponds to the y value. If you notice on our graph, there are no y values below 0. There is no graph below that x-axis, right? So the y values are all from here up. I have a y value at 1/4, 1/2, 1, 1.5, 2, 2 3/4, 3, 3 5/8, whatever. There's y values all along there, and there's y values all along here. And notice that for every y value over here, I get another one over here. Okay, different x values, which means this is a function. Same y values actually means that it's not 1-to-1. And I think we get into that more when we get into parabolas later on. So the range, we can say y is greater than or equal to 0. One way to say it. Because here the y value is 0, and it goes on and on and on and on. If I plug in, 250, the absolute value of 250 is positive 250, and it's going to be, somewhere up there. Another way to write this using bracket notation is to put a bracket, 0 to infinity, parentheses. The bracket means that 0 is included, and whenever we end or begin with negative infinity, infinity, or infinity, we always put a parenthesis with infinity, because it's not a number, it's a place. And so we don't use, it can't be infinity, but it can approach infinity. So when we're using infinity, we put a parenthesis. If the 0 were not included, we would put a parenthesis. Okay, so there you have it. There's the graph of the absolute value. What we want to do with this okay, we're going to graph this one. Okay, so again, I'm just going to plug in some numbers. I'm going to plug in 0, and I get 0. I'm going to plug in 1 for x, and I'll get 1/2 for y, because we're graphing 1/2 times the absolute value of x. The absolute value of 1 is 1, times 1/2 is 1/2. If I plug in 2, the absolute value of 2 is 2, times 1/2 is 1. And so for that reason, I might skip 3. I might go ahead and jump to 4. The absolute value of 4 is 4, and 1/2 of 4 is 2. I'm not going to be graphing fractions. Now, of course, I need to know what's going on the other side, right? And I could use the axis of symmetry to determine that, or I can just plug in -2. The absolute value of -2 is +2. 1/2 of 2 is 1. I could plug in -4. The absolute value of -4 is 4, and 1/2 of 4 is 2. So let's see, 2, 1, 3, 4, 2, -2, 1, and -4, 2. And that is my, oops, that's going to start off bad. That's my graph. And if you notice, what it did was it took that parent function and it stretched it out. It made it wider, it made it flatter, you know, whatever you want to say about it. And in fact, as this 1/2 approaches 0, 1/2 changes to 1/4, 1/8, 1/16, 1/32, the flatter and flatter this graph will be to where it's almost going to look linear at some point. Okay, that's what the number in front of x does to the graph. Okay, so there's our graph, the domain, all real numbers, the range, y is greater than or equal to 0. There's nothing I can't plug in. The domain and range is the same as what I have for my parent function. Okay. We're going to go to h of x, or y equals -2 times the absolute value of x. Okay. So again, I'm going to plug in some values. If I plug in 0, I get 0. If I plug in 1, the absolute value of 1 is 1, times -2 is -2. If I plug in 2, the absolute value of 2 is 2, times -2 is -4. If I plug in -1, I get the same thing, -2. If I plug in -2, because of that axis of symmetry, I get -4. 0, 0, 1, -2, 2, -4, and I can either use my axis of symmetry or plot the point. This is what we get. And so talk about this. This graph is skinnier than what my parent function was, if you notice. It's not as flat. And in fact, that number in front, as it gets larger, skinnier and skinnier this graph will become. Okay. The negative takes the parent function, which would have been up here, and puts it down here. And so it flips it over. What that does to the domain is still all real numbers. The range is different now. The range isn't greater than or equal to 0. The range is less than or equal to 0. And to put that in bracket notation, we would say that the range is from -infinity to 0. The 0 is included, so we put a bracket. And the reason we put -infinity to 0 is because usually when we write the range or the domain and it's in numbers like that, we write it from smaller to larger. Okay, so that's what we've done there. Here's what we want to be able to do with absolute value. Okay, Jay rides in a boat from his home to his friend's home in a neighboring state. Okay, the graph of the function given by the equation shows the distance of the boat in miles from the state line at t hours. And what this looks like is, you know, here's our lake, okay, whatever it is, here's our lake, and here's the state line, okay, and this is Utah, and this is Arizona, and the friend is in this boat, right? I'm trying to draw a boat. I'm not doing a very good job. Maybe it's a sailboat, okay? And he's traveling from Arizona. He's going to cross the state line and into Utah, okay? So how far, first what we want to do is we want to graph this thing. Okay? And I've done that down here, okay? So when I plug in 0 to that, I get 1.5 times 30, which is 45. When I plug in 1.5, I get 0. When I plug in 3, I get 45. Okay, so there's the graph of that function, that absolute value. All right. How far does J travel to see his friends? Well, he begins his trip 45 miles from the state line, travels towards the state line, which he crossed after an hour and a half, and then he traveled from the state line, was 45 miles from the state line after 3 hours. Okay? So the way that's depicted on this graph is just that. He started 45 miles from the state line. He traveled to the state line in 1.5 hours, and then he crossed the state line, and he had traveled away from the state line to his friends in Utah another 1.5 hours for a total of 3 hours, and he was 45 miles from the state line. So how far does Jay travel to visit his friend? 90 miles. 90 miles from the state line, cross the state line, through the state line. Okay. How does the graph relate to the domain and range of the function? So the domain here, and we're not going on. Okay. So this is a finite step. The domain is obviously from 0 to 3, because that's when he reaches his friend's house. So notice I didn't, extend this out and put an arrow on it, and I didn't extend this out and put an arrow on it because it doesn't exist. Okay, the graph is from 0 to 3. That's his traveling time. Okay, so the domain is 0 is less than or equal to t is less than or equal to 3. If we were using bracket notation, we would say bracket 0, comma 3 bracket. The other thing they like to talk about with this is where the graph is. Well, let's do the range first, and then I'll get into that. So the range, again, finite set, ranges from 0 to 45. And again, we don't go beyond 45 because that's what we travel. Okay, so the range is 0 is less than or equal to d of t is less than or equal to 45. Or if we were using bracket notation, it would look like that. When the domain is 0 to 1.5, the function is decreasing. Okay, as time is increasing, the y values are decreasing. So the function is decreasing. Once we hit the state line and we start going beyond the state line, then the function is increasing. Okay, increasing this way. So from the graph is decreasing from 0 is less than or equal to t is less than or equal to 1.5, and the graph is increasing, the function is increasing from 1.5 is less than or equal to t is less than or equal to 3. Okay. So then what we like to figure out with some of these things, it's called the rate of change. Okay, what's the rate of change over the interval 2 to 2.5? And rate of change, I want you to, whenever you see rate of change, I want you to think of slope. Rate of change is the slope of the line on that interval. Okay? So on this interval at 2, okay, here's the point 2. If I plug in 2 to our equation, okay, 2 minus 1.5 is 0.5, and 0.5 times 30 is 15. So that ordered pair is 2, 15. Okay. And the ordered pair at 2.5, if I climb up here to 2.5, and again, not again, I guess is the first time I'm saying, I could go look over and see, okay, what's that landing on? But I don't trust the accuracy of my graph. If I were using the graph in the book, I would trust the accuracy of my graph, but I don't have lines on here. I just drew this somewhat freehand, so I would rather take the 2.5 and plug it into the equation and figure it out. So 2.5 minus 1.5 is 1. And the absolute value of 1 is 1 times 30 is 30. So that ordered pair is 2.530. So to find the rate of change on the interval 2 less than or equal to t less than or equal to 2.5, find the rate of change on that interval, what I'm going to do is I'm going to find the slope between the point 2, 15 and the point 2.5, 30. So slope, we're experts at slope. Slope is 30 minus 15 over 2.5 minus 5, or 30 minus 15 is 15 over, should be 2.5 minus 2. I'm not being such an expert on slope, am I? 2.5 minus 2 is 0.5, and 15 divided by 0.5 is 30. Okay. So the average rate of change over that interval is 30. And what that means is the rate of change represents the speed of the boat in miles per hour. Since the rate of change is positive, J's distance from the border is increasing. The boat is traveling at 30 miles per hour away from the border. And this is what leads us up to study. We don't call it these things per se. We do say rate of change, but eventually we get to AAVideoT, which is the velocity from the position. This is what's leading us up to calculus. And that's why we take algebra 1, because I assume everybody's going to take math classes, and this is your preparation for such, as well as your preparation for tests that are going to help you get into college, or if you aren't going to college, tests that are going to help you become an apprentice in electricity or plumbing, or you have to pass an algebra test to get into those apprenticeships. But anyway, I digress. So then my last example here, how do we find the rate of change over the interval up here? From the graph below, what is the rate of change over the interval from 15 to 18? And I have those points marked. This is at 15, 3, where it's supposed to be on the y-axis, and this is at 18, 5, where it's supposed to be on the x-axis. So the rate of change is the slope. We'll find the slope between those 2 points. So I take 5 minus 3 over 18 minus 15, and I get 2 over 3. The rate of change over that interval is 2/3. And we don't know the units on this one because it's not a story problem. Just here's the graph, find the rate of change. And to find the rate of change, we find this problem. Okay?